Okay, now it's time to move on to discussing the other problems. In the first problem, the importance of the first problem was that we did a massive thing. We actually learned how we can estimate impulse response with loops. So the system with loops that we can develop will have the flexibility for you to pass on as many of rows and columns you autoregressive and moving average lags you want, and the system should automatically adjust itself to estimate as much as it can, okay, now it's time to move to the second problem. Rows, columns. Okay, second problem, SVAR Shortrun, and let's see, open the second problem, Shortrun. There's not a lot of problems in this chapter, but all of them are defining factors or brings closure to your understanding of structural models. And structural models are the, what should I say, beginning in the econometrics. Consider a system of three interest rates where R1t is the instantaneous yield, R2t is the 1 month yield, and R3t is the 3-month yield. The structural model is beta naught yt equals beta 1 yt minus 1 plus z by root over d. Z by root over d, as we are familiar with, root over z root over d, I'm sorry, root over dz, not divided by. Root over dz, where the short run restrictions are beta naught 1 0 0 minus b2 to 1 1 0, because taking things on left hand side. This is the residual equation for variable 2, residual equation for the third variable 0 minus b3 to 3 2 1 second variable, and the third variable in the second column. Second variable first column, third variable in the second column, or by rows as well. And diagonal elements using monthly data on United States 0 coupon yields from December 1946 to February 1991. Estimate the parameter of the models by maximum likelihood and test the number of over identifying restrictions. But before we move into that, there is just one function that we need to introduce ourselves to, which is, I think, where were we? No, let's see. Yeah, wow, bullseye, we are in the right page. We're gonna use diag rv function, which puts given vector onto the main diagonal of a square matrix. So a vector is put on the diagonal of the square matrix. Reproduce the Gauss command tag rv, assign values on the main diagonal. So we are assigning the values that we estimate for a vector on the diagonals, only on the diagonals of a square matrix, right? The function itself is xv. So vector, x will be assigned on the diagonals of v. So x minus diagonal of x plus diagonal of v, diagonal of x plus v. So whatever this position makes the upper triangular, this portion is making the upper triangular 0, and well, x minus is giving you the position is being placed. So to be straightforward with this equation, you have your matrix placed, your vector placed on the diagonal elements of V. That's all. let's get back to our problem. There is one thing before we move on. In the previous problem, very important problem that we talked about, after impulse response, we didn't show you how to do the graph, right? And maybe that's not very important for now, because we want to plot basically our graph from our impulse response functions. We can simply do it if we take the columns and represent the columns without any loops or anything. In this problem, we try to do the solve the plots in loops. It's not at all important. You can simply, create your pictures or your plots manually. Okay, so we're not gonna focus on this at this stage. It's not that important. The code, the main function is more important than anything else. So short run restriction, and we have talked about the question, and we need to estimate the parameters of this model. Okay, so let's see, what do we do first? Do we have function? Yes, we do. First of all, our equation, the function is neglog v, number of rows v and number of columns. Then we are suggesting what our equation will have, whatever the reason it is. This could have been in this place, but not necessary though. So minus b0 1, instead of that we could have done 0 minus b1. Will that matter much? Probably not, because we're just estimating our parameters here. So matrix is being created with all these elements with number of rows 3, and that will be created by rows, not by columns. Structural, residual and variances, diagonal elements, where you have x and v. X is identity matrix, which is the size of number of columns. Identity matrix will be created as per number of columns, and these identity elements will be placed diagonally on v, and v is our beta parameter. Absolute, we take the absolute value of the third 1 2 3. So from the third to the fifth element, so we are taking the third and to the fifth element, 3 4 5. So taking b, not beta not. So we are taking beta parameter, b parameter. Our parameter that we have to estimate is b, and we have second, third. What are our parameters? We need to know our parameters here. Third, 3 4 5. 3 4 and 5 are our parameters to estimate. So we have a diagonal elements are from 3 to 5, right? Let me understand this. The question is answered. In our beta naught, you see our two parameters are beta b21, b32, then d11, d22, d33. So here these two elements are being estimated in beta naught. Then we want d11, d22 and d33. Those three are the third to the fifth elements. The three elements, we take the absolute values of the third 3 to the 5 element. Basically we are actually estimating v, and we are placing them in the identity matrix, right? So we have x and v. So we have x is a matrix, v is a vector. So we have the vector estimated, which is absolute value of the third to the fifth element, and then we are just putting them in the identity matrix, the diagonal element of the identity matrix, so that we get the shape exactly as this. So diag RV, the matrix where whose diagonal elements we will be replacing with this vector. Then S is equal to root over d by v naught. So beautiful. And variance covariance V is equal to SS transpose. The omega is equal to SS transpose. Then comes our log likelihood function, and the log likelihood function here is 0.5 log twice pi, 0.5 log determinant of the omega, and 0.5 V transpose inverse of omega. We are familiar with this equation, so that's what we have done, 1 to t, and taken the negative log. Return SVAR matrices, right? So this was the log likelihood function, and then we want SVAR matrices. So beta naught ds vc naught will be well returned, I guess, and we will input b and v. So all rows in column is the size of v, just the column we need. Beta naught is there. Structural residual variances. Now what are the outputs here? Here the outputs are, these are the inputs. V and V are the inputs, and it will return, this is returning the log likelihood function. This on the other hand returns, these are the outputs, beta naught ds vc naught with b and v. So we have estimated b and v already beautifully, and we use that b and v for this equation here. Basically we just want more information, which is we want our beta naught matrix to be estimated by the system as var structural var matrices. We want the diagonal elements, we want S and VC naught for the system to estimate, right? So equation is the same. So let's see how we call for both of these function. So we have US model of interest rates, and we estimate a var with one lag. We are doing this old fashioned estimation. We could have done the new fashion estimation instead of the old fashioned one. What is the new fashion? Is always good to keep the first equation open, which is SVAR by variate in both cases. There's no point showing you where the files are, so I'm just gonna pause it at this stage. So without the loop, a var with one lag is estimated in this manner, which is our old-fashioned way. So column bind, replicate first the constant, then a level and lag, then regression. We could have done this in the new way, and the new fashioned way was, well, 1 to p. First we set the constant, which is 1's length of y1 for the loop, right? And number of constant, we could have set the number of constant, then we could have taken as much, we could have gone for up to number of lags, and we could have represented with level y lag 0, then the lag, okay, 0 instead of 0 1 0 I, because this is a var with one lag. If there was higher order lags, then 0 I would have taken care of the situation. Then this could have been our x, and then we could have taken the regression, which was, yeah, so the level on the lag, right? So regression of x, the level yp0 on the lag, so we could have done that, is the same thing. yt10 regression of the level on the x variable, and you know, we could have found our v, which was again the level minus x into a, or beta into, or yeah, here we are doing ax, beta into lag, and number of rows. So we could have used, it would have been easier to use, it would have been better if we could use the system, automate the system as the process goes on, you know. So the steps were very simple. First you represent the first row, the first function is to make sure that your data is stored and the number of constants, and then things change as per the number of constants, right? 1 to p, for 1 to p or 1 to row, starting with level ylag 1 0. So x is ylag 1 0, which is actually ones, number of ones, and 1 0 I, and then this very simple thing. So this is how we could have actually done our actual this part, estimate of var with 1 lag. Then comes estimate SVAR, right? Because we have already defined our function, we're gonna call our functions now, and our theta is 0.1 multiplied to 1's 5 rows 1 column. Why 5 rows 1 column? Because we have 5 unknown parameters here, right? And we're gonna call for the first equation, first function, neglog vv theta naught optimization. Neglog vv, are we calling neglog vv or neglog b? Oh no, we are calling for the log likelihood function SVAR. So we're calling for the optimization par neglog v equals v and Newton-Raphson algorithm, and we have the log likelihood function value estimated to us negative f-val, okay, b negative f-val, and var parameters, variance, covariance, and then we want to also compute SVAR matrices. And now we call the matrix beta naught d is from function of vv. Just running this equation automatically, interestingly, give you the S matrix, the FVAR matrices. So S matrix is function of vv. We are telling that the whole thing is structural matrix. Beta naught is the beta naught portion, d is this column, this column. That's real, very simple. Wow, we are done. Short run. And then comes the next problem. A model of interest rate with long run restrictions. Now consider a system of 3 interest rates again, where the interest rates are instantaneous yields, using monthly data on the United States, 0 coupon yield from December 1946 to February 1991. Estimate the parameters of the structural VAR model by maximum likelihood using the long run restrictions. Okay, so this is where the restrictions are, and this is our unknown parameters. We need to test for our identifying restrictions, and the problem is SVAR long run. So let's look for SVAR long run. We have SVAR long run. We have from here we have SVAR long run. Obviously we'll start with the function indeed, and what are our unknown parameters that we have to estimate? V, and what else? Monthly data 20 parameters. Oh, we also want to estimate our phi1 autoregressive parameter. Why? Because S is equal to phi1f. Very simple. So t rows and n columns, we are placing our equation in the matrix. Then S is equal to what? Identity minus A1. So because phi L is 1 minus phi 1 minus, so obviously the first one is identity matrix for 3 parameters, minus A1 into F, and variance covariance matrix. Then we call for the log likelihood function. So diagonal 3 gives you identity matrix. Okay, so diagonal 3 minus A1 into F, then we have omega, which is SS transpose. Then the log likelihood function is as before. The last one is column bind, and taking the and SVAR matrices as well, just like before. Nothing changes except for what we want. We want F, we want S, and we want VC naught. Okay, sure, fine, no problem. VC naught will help us to probably understand if our restrictions to test, actually VC1 minus VC naught will help us to test probably. Yeah, so start with importing the data, then the growth rate. Then again we are doing the old-fashioned way. We could have first, suggested done this thing with loop, because first we could have taken once, to store our data, and then we could have taken y lag, isn't it? Like what was that looking like? SVAR by variate. Sorry. Keep forgetting all the time. So we could have taken a number of constant, could have defined number of constant, and then by size function, then we could have taken y lag with the level. First we could have had the level, which are the ones. Yeah, because we could have done the level and then the lag. Okay, and then we could have so we could have taken ones and then the lag, and then they taken the regression against the level. So ones, lag, and level, and that's all that we could have used. Again, in my case I'll do that. I'll do the loop one, so the system is automated. So x would have ones, so ones, y lag 10, y0 I, y lag 10. Yeah, sorry, it's for long run. Yeah, 10, then y0 I. Then we could have done the regression, and same thing would have appeared. So with one lag, and then lag 1 autoregressive parameters. Let's get back to what we are talking about. Long run. And then lag 1 autoregressive parameter is A10, because we have estimated A with the lag 1 autoregressive parameters is simply A10, A1 trim A10, which is b plus ki minus 1 to ki. B plus ki minus 1 to ki. What we are doing here is much simpler. Trimmer A10. Basically we are saying that all the autoregressive parameters are stored except for the constant. We are taking all elements which are all autoregressive parameters. We are not estimating yet because we're letting the system estimate, right? Indeed, because we have created a function already for a1, so a1 will be automatically estimated with the function. Manually you could have done the function with 2 stages. First lag defining, then a1 minus phi 1 minus phi 1 minus the reshape I kk, if you can remember, t minus phi 1 minus t minus 1, the same thing. So estimate SVAR is called the function. It will automatically do the estimation. And compute the SVAR matrices simply as before. You see, the system is automatically estimating all the parameters, and when it does, we just remove the first constant and we have everything else. We are left with our autoregressive parameters. So first we start with var, then we let the system move on from there, take over from there. So the first stage is always estimating the parameter for initialization with OLS, then it moves on. So long run, short run, in both cases they are the same, no changes except for defining what goes into the matrix, that's all. Then the next problem is the extended Sims model. Consider the 6 variable Sims model where R is the interest rate, E is logarithm of exchange rate, logarithm of commodity price, logarithm of money, V is the logarithm of price, O is the logarithm of output. So you have 6 variables. The data is given. Estimate a recursive structural var where the var has 14 lags, a constant, 11 seasonal time variables. Choosing the ordering in this manner, compute beta naught D and hence S is equal to beta naught inverse D. Use the reduced form from Kolesky decomposition. This should be fun. Okay, let's see SVAR Sims. And what we just did, SVAR Sims. No function. So first you bring in the data, make the matrix, then var with 14 lags. Well, this is another different approach. We could have simply estimate our var with whatever we learned before. Here we are doing v equals 14 lag matrix. Lag matrix creates, as you know, one level and one lag, then one level and one lag. So if you have multiple level and lags, it will create a matrix in a recursive matrix, right, where the upper elements will be all zeros or non-values, no values. So it is creating lag matrix. I'm not sure if I have to show you lag matrix again, but let me still, just if in case you have forgotten, this is how lag matrix is created. X, lag 0, lag 1, first element is none, lag 2, first 2 elements is none, that's all. So 1p and y lag, if any is none, anything is 0 in our y lag, in the columns, second dimension, in the columns we put them to be 0. So lag matrix is the function here is lag dot matrix, and y lag is -1 to row, which will adjust this y lag -1 to row. What we're gonna do is that from the beginning we're gonna remove from 1 to row. So column bind x is 1s, then dummy variable 0, then the dummies is term 0 to row, and then y lag and trim her y0 row 0. This could have done with the previous way that we did. We didn't need to create a var like this. We are giving it a recursive structure, but it's not necessary to follow this method. Anyway, this is another method that we can use. Okay, and it is kind of without loop. This is an easy way. Another method was that we talked about earlier. Trimmer y lag 10, trimmer y0i could have done in this manner. You know, this is what we did before. Okay, we took the regression and we estimated the method, the stuff. This would have been giving me the same result, and it would have not mattered at all. Though I'm suggesting the dummy variables separately, and that might be a problem. So this might be the only reason for which we might need to follow this lag matrix structure, because we're not taking all the elements of our matrix, we are just adjusting along the dummy variable. Yeah, makes kind of sense, right? Okay, then we are gonna come back to reduce form approach, residual. Then phi1 is u1, u2 regressed on u1, regressing u2 on u1. u2 is then the residual again. u2 is this regression coefficient, u2 is regression residuals. u2 minus u1 into a2. Then we are doing, moving on, basically we're doing for the rest all the elements and blah 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 up to u6. So we are finding 6 residuals and 6 coefficients, and then we create our matrix with these 6 elements and residuals, and beautiful. Cholesky decomposition approach, on the other hand, we simply take Cholesky, transpose it for, you know, representation. Then we do S minus diagonal of S transpose. Diagonal of S transpose, because here we have already taken transpose on the Cholesky decomposition. So here we already have, with Cholesky we have the diagonal elements or the eigenvalues, and we are dividing those with our diagonal element of S. S1, apply S, I don't know why it's 1, anyway, X margin, then the function, right, X margin, margin 1, that means lag, so there is no lag, so 1, then division, then the diagonal, that's all. Apply, taking the inverse, and diagonal element is, we have identity matrix along the row, along the diagonal elements, we put the diagonal S squared, and beautifully we have DCD. That's all. Cholesky decomposition approach, very simple. So BSX1 and applying BSX1 is at the rate of R divide, where we are doing R divide with 2 element S and diagonal S, X and Y. However, we have a margin to set, which is 1, which is the number of lags you might have, nothing else. So this is Siem's approach. We have reduced form, beta naught, we have Cholesky decomposition, beta naught, not much of different. The only tweak is that when you have the dummy variables set separately, a lag matrix method way is a better way. If you don't have dummy variables, then you could have done the regular lag estimation as you have done before. So you have seems solved. Then the next problem, but again this calls for a coffee, and so small break. Number 5, the Pearsman SVAR model of oil price shocks. So consider a 4-variable model of the United States containing the growth rate in the oil price, the growth rate in output, the inflation rate, and the interest rate. The structural shocks comprise oil price, aggregate supply, aggregate demand, and money shocks. I need to estimate the VAR with 3 lags constant and a time trend using data from blah blah blah. Estimate SVAR subject to restrictions. The 3 non-oil price shocks are these: do not have a short-run effect on oil price. The money shock has no short-run effect on output. So these are the restrictions where the oil price shocks do not have short-run effect on oil prices. There is no short-run effect on oil prices from the shocks. Money shock has no short-run effect on output. Aggregate demand shock and the money shock have no long-run effect on output. Compute impulse responses for oil output and price and interest rate. Interpret the results. Verify that the impulse responses are given by S at h is equal to 0, short run, and by F with h is equal to 100. Okay, so that is a Pearsman model of oil price shocks. Let's see how it is done. Pearsman. Is there any local function to begin with? Yeah, there are. The first function is to define the log likelihood function, and yeah, log likelihood function is we are taking so wrapper function for log likelihood. So minus sum, why not mean? See, this is an error here. Minus mean, BV, and autoregressive parameter. Okay, log likelihood function taking the moving average parameter here, A1 inverse. I can obviously inverse it to get the autoregressive parameter, it's not a big deal. T rows 1 column. Long run restrictions, you have S43 where you have minus, so these are just the restrictions, how these restrictions are coming in. Okay, let me help you with this task. So this is how we are setting the restrictions, 513, 512. So in both cases we're dividing by, S22 is 512, S23 is 512. So basically S12 from short run restrictions, this is how we do it whenever we are doing. So you write down the whole equation, then you just take the particular S you want to estimate. So this is how I want to estimate S43. So after from the full equation, I'm just writing this down, not a big deal. Sitting on S, omega is known to me, 1 to T, log likelihood function defined. That's all. Any tweaks? No tweaks at all. Just C bind, column bind at the end. There is the only function here, local function here, then number of logs, and this is beautiful. The way that we have defined before, y lag is once, then length of y transpose. Why am I doing this like that? That was not necessary. However, okay, because I have a constant and a time trend. Constant is fine. Lags and constant we have worked with. We have not worked with a time trend in terms of for loop before. Because we have not done with a time trend before, so this is the time trend. So once up to length of y will have once here. That will grow by 1, sequence and rowing sequence, right? Grow by 1. Constant is, we already know what constant, we have already used that is the regular loop yt minus 1, as we know. The lag and the level, this is just once, and the level, which is should be x here, and y is the level, and estimated that we have omega, blah blah blah. Constructing autoregressive parameters just like before. Okay, beta, we have beta number of constant, rest is from there we are finding the number of columns here, which is the number of variables. So n square, this is n variable, this is n square. Matrix, structuring the matrix here. Then identity matrix, we will be needing that. So for y is equal to 1 to p, we'll play with a, right, because this is the structure that we have set. So yt minus 1 till yt, up until yt, beta will continue just like before. Then we are taking the elements, placing them here in that structure, all rows, I columns, and then we are reshaping, because this is phi 1, which is 1 minus phi 1l, right? 1 minus, this is 1 minus phi 1l, this is phi 1l, because same thing, you have phi 1, you have phi 1 already estimated, but structured, reshaped, that's all. Then inversing it, we have initial value that we are passing ourselves. Display maximum function evaluation, we want to maximum iteration will be 2000. Wow, we want to go for maximum evaluation, maximum functions will be 4000. Then other stuff are there where none of this is required in R. So call the function, run it, you have log likelihood function that estimated beta. So now we estimated beta from maximum likelihood estimation. Okay, unlike previously, we're estimating beta with maximum likelihood estimation, and we are going to use this beta now. We haven't used beta yet. We used for autoregressive parameter, we use OLS estimation. Are we gonna use the maximum likelihood estimated beta? Probably. Let's see. In moving average is just as we have done before, all elements basically 1 0 1 0. We have psi naught, which is an identity matrix, then 1 to q, for 1 to q we used while. Oh yeah, we are going to use while again. Yeah, 1 to q, zeros created for kk. So start with 1, that will increase by 1, which but the function terminates, so that will update by 1. A minimum of pi, so minimum that will reach the minimum of the autoregressive parameters, so that they don't converge. That's what we don't want to for our moving average parameters to converge to autoregressive parameters. So SS is psi naught, which is identity. Then it will move on. No, this is not identity, I'm sorry, this is identity. So we'll start with zeros and reshaping phi 1. So psi 1, we remember that, right? Phi I is equal to psi I minus 1 to the power I plus 1. Phi I is psi phi to the power I equals phi I is equal to psi to the power I, right? What was the equation? Just very quickly, yeah, phi I equals psi 1 to the power I minus 1 to the power I plus 1. This is psi 1, which is phi 1 itself, but this is the sign, minus 1 to the power I plus 1, minus 1 to the power I plus 1. This is minus 1 because C is identity, so we are just playing with the identity here. Explained all of this before to you. And then we have identity and our moving average parameter. Then we do impulse response function. We are again coming back to the SS that we estimated S. Okay, impulse is taking, we have estimated S, then impulse is vectorizing S, we are taking the vectors. Then we know impulse is 0, I equals 0 to h minus 1, or I equals 1 to h, 0 to h minus I, or I equals 1 to h, right? So equals 1 to h. We have a var2 system here, so equals 2 to h, right, which is q plus 1. Why? Because q equals h minus 1, q plus 1 equals h. Very simple. So I equals 1. You had 1 to q or 2 to q plus 1. That's all. Sorry, I equals 0 to h minus 1. Yeah, 0 is 1 to q or 2 to q plus 1. Right, correct. But 2 to q plus 1 is what we use. So impulse is simply, again, we took the elements C and that is reshaped, and we multiplied that with S, psi I S, or in other words, psi h minus 1s or psi I S. And we have the impulse response function created for us. Then we need to construct the variance decomposition. And is there any game in variance decomposition? Yeah, variance decomposition equation suggests, so let's go back to page 2. Variance decomposition equation suggests two impulse response functions having Harder-Mark product, or psi I S or psi I S S transpose. So this is what it is. Let's see how this is done. Variance decomposition is, first TMP0 is I 1 to n minus 1 to q rows, q into q rows, k columns. So taking the complete variance decomposition, we are taking impulse response, which is 1 to n minus 1 rows. So level 1 to, no, sorry, lag 1 to n minus 1 rows, 1 to n minus 1 rows. Basically, impulse response function is psi h minus 1s for all columns, which is squared, element by element squared, because IRF squared q by k rows, that will go up to q. That will go up to q, 1 to h minus 1 rows, q by k rows, and k columns, q into k rows. So q is moving average, and this is based on moving average, right? This is based on moving average. So this will go on as per moving average rows and k columns. Repeat matrix TMP1 is the repeat matrix. Sum of TMP0, we take summation. Now we keep adding. This is defining this equation, and then we are adding. Now TMP1 is adding. Sum of each one by columns, one row, k columns, up until k columns. So we're gonna repeat that, and then we are gonna reshape the whole thing by dividing q into k square. Decomposition is q into k square, right? I'm not sure what they did here. So basically, this is the element 1 by k, repeat matrix, and then TMP0, this one divided by this one, Q rows, K square columns. Obviously that will be K square columns because N square, that's why N square columns. Q rows, structure is fine, so decomposition is K square columns based on impulse response, right? So taking cumulative sum, apply trimmer, impulse 0 1 squared, so this is just impulse h minus 1 squared, we take up to 2 lags here, right? Margin is 2, before margin was 1, that this is var 2, so margin is 2, which is K. N equals K, no, N is much bigger, Q equals 2 probably, yeah. Cumulative sum, margin is 2. Okay, taking 2 lags, Q by K rows, that means if they have 2 and 4 variables, K columns, Q into K rows and K columns. MATLAB function is a bit more difficult here. And this was summing, this was moving forward, summing stuff up. You done this, then you're you done the multiplication, then you're summing them up. That's all. You done the multiplication, and then decomposition is represented in by reshaping it. 100 is not necessary, maybe we want to change the dimension, that's all. TMP0 divided by TMP1, Q rows, K square, N square column. That's moving average amount of rows, no matter how many moving averages you have. So this is the variance decomposition, and this is what we did for the first time. Good learning. First is, one more time, first is this function psi I S1, because psi I S1, so impulse 1 10 minus 1 squared, Q by K rows, K columns. Dimension is the game, which is Q by K rows. Q is number of moving averages, K is number of variables, so that many amount of rows and number of variables columns, structuring them. Then we are summing them up by columns, not by rows. We are summing the whole thing by columns in one, and we are repeating each row K times. So what we are doing is, let's repeat the stuff and sum them up. Sum is by columns, yeah, summing them by columns, repeating one more time, and then using to divide it, Q K square, which is N square. Oh yeah, because we didn't have N square here, because decomposition is not only moving average, it's also autoregressive. So for this we need to repeat the matrix one more time, and then we need to divide them, because decomposition requires psi I minus, basically there's a relationship between autoregressive and moving average parameter. That relationship is established. What was the relationship? Hey, why not? Psi equals phi j, psi I minus j. So that is kind of the relationship, phi j, psi I minus j. So we can write decomposition as this, dividing them q square. So just memorizing. Some things require memorizing. It's very difficult to some extent, but very important. So variance decomposition, you have it. Okay, Pearson done. The next problem is a portfolio SVAR model. Consider a 5-variable portfolio SVAR model of Australia containing output, interest rate, real Australian equity price, goods market price, realty. 1, 2, 3, 4, 5 variables scaled by 100. So we just scaled them by 400. So multiplied the last decomposition case, scaled by 100. Which is this problem? Portfolio SVAR port. We have this SVAR portfolio. Using quarterly data from this period, estimate a var containing a constant 2 lags, a dummy variable corresponding to stock market crash. Maybe we'll need to do lag matrix because of the dummy variable, and to dummy variable to capture the introduction. Estimate a port var model for Australian economy where identification is based on long run restrictions. Interpret impulse response function and variance decompositions. Portfolio model in part B is based on the restrictions that an aggregate demand shock simultaneously raises interest rates and lowers real equity value in Australia. Use the LR statistics. We are familiar with this. We'll just go very quickly. Any functions local is stub. Yeah, there is local function. Restricted SVAR model. Function is set. Why we are saying restricted? S is equal to a1f omega blah blah blah. Function for restricted SVAR model, right? Something must be restricted here. oh sorry, long run restrictions. S is equal to a1f, that's what it is. Any other function for unrestricted? Zeros t1 long run restrictions. Okay, in terms of the function we'll have the difference. No, b1 b2 b3 b4 b3 b6 b12 b5 b13 b6 b12 b7 b8 b9 b10. This is an error or nothing else. Where the restriction is coming again? So what restriction is set against crash and no crash? Alright. Restricted is minus b13 is restricted. No. So this is the element where the crash happened. Yeah, everything else remains as it is. Nothing changes. 1987 stock market crash. A dummy variable. So there is a dummy variable b13. b1 b2 b3 log st. Just where Australian equity prices, stock prices, and stock price crash. So restricted and unrestricted are set like that. b3 and b13, that's the game. We go back to the actual code. We bring in the data, create the matrix, create dummy variables, stock market crash, DST introduced M variables, zeros, 102 rows, 1 column, and then we do the regular. So see, lag matrix was not necessary. That what proves here, even with dummy variable, so it's not necessary. Instead of using lag matrix in Y lag, we introduce the dummy variable. These two dummy variables, we are introducing them. That's all. That's the whole thing. Column bind. Dummy variable is introduced here. Beautiful. Then we move on. We do as we have done before. Then after moving average, we call the function maximum. We estimate unrestricted SVAR. BVA1. I'm not sure why they are doing it twice. BVA1, BF value. Restricted log likelihood function. Well, where is the restriction coming? Here, let me check. Let's just compare. See, with this 1, 4, 5, 10, 2, 1, minus 1, 7, 1.6, 10.75. Is this the restriction place? No, 10.75 is there. 3.5, 10.75, 3.5, minus 5 is not here. Instead of minus 5, what are we using? Minus 5 is not here. 10, 1.3, 1.6, 1.7. So the last element is not included. The last parameter is against which we are putting our restrictions. What is our last parameter? Autoregressive, moving average parameters. One, two, three, 4, 5, 6. Let me go through the question one more time. We have 1, 2, 3, 4, 5, 2 lakhs and the dummy variable. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 2 lakhs, a dummy variable. And a constant. The constant and the dummy variable. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 2 lakhs, constant, and 2 dummy variables. 1 dummy variable. Alright. Alright. That's what suggests restricted and unrestricted. Dummy variable to capture the introduction. 2. So one captures the crash, one captures the GST introduction. So we are checking against GST introduction. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 10, 11, 12. 13 was the game, right? In our equation. If you go back, 13 is the 13th dummy variable is 3. So in place of 3, place 13. Okay, got it. Clear now. So that's how the restriction is done. Likelihood ratio. Why we are not doing it now, and why you are not doing it at the end? Because it doesn't matter. It depends on autoregressive parameters that we have already estimated. Moving average parameters with while and end as before. Impulse response function as before. no changes. Then variance decomposition, just as before, exactly as before, scaled by 100. Repeat matrix. We don't need to follow this, we can follow whatever we learned just one program before. We can do that program. This is, I mean, breaking things into more smaller parts. So we have the variance decompositions, and then we can just plot them, that's all, with subplots. And there you have it, portfolio decompositions, which is a portfolio SVAR model. And what we just did, we estimated portfolio SVAR model, impulse response and variance decomposition, and we did likelihood ratio test on aggregate demand shock on this. B is based on this aggregate demand shock. Simultaneously raises interest rate and lowers real equity value. A demand shock will increase interest rate and lower equity value. Something like this, against which we have created the metric restriction. Then there is Okun's law, goods market shock using sign restriction. Maybe we'll just look into sign restriction. Not Okun's law might not be that much needed. So this is again in terms of Okun's law is suggesting where to put blanket Okun's law is against blanket core model. So doing a blanket core model, Okun's law is simply restrictions. Not necessarily. We just want to look into sign restriction first. Consider a bivariate SVAR consisting of the annualized quarterly growth rates in output and prices. Sign restrictions are used to 400, scaled by 400, are used to identify aggregate supply and aggregate demand shocks. When aggregate supply shock has a positive effect on output and a negative effect on prices. Supply shock has a positive effect, so what we are looking for is that it will have a positive effect on output and a negative effect on prices. Aggregate demand shock has a positive effect on both output and prices. So 1 minus 1, 1, 1. Positive effect on output, negative effect on prices. Demand will have positive effects on both. Estimate of VAR using quarterly VAR is specified to have two lags and a constant and a time trend. So an additional time trend will be added to our system. Residual covariance matrix is this. Now use this to compute S based on Galeski. Impulse response. Do not confirm when shocks corresponding, so maybe impulse response will not confirm, so regular impulse response. And then change it with Q transpose with gamma 0.2, and now it will respond to it, generate 100,000 simulated values from the interval 0 to pi and select the set of impulse responses for each draw. Compute the median impulse response from the set. In computing the median, it is important to ensure that the 4 impulses chosen come from the same model. Otherwise, the shocks are not orthogonalized. 4 impulses. The approach adopted is to extract the contemporaneous impulse value from the selected impulses and group these values into 4 impulse sets. These are each standardized by subtracting the respective median and dividing by the respective standard deviation. The median set of impulse is taken as the model that has the smallest absolute deviation from summing across the 4 impulses. The median set of impulse is taken as the model that has the smallest absolute deviation. So looking for the model which has the smallest deviation across these 4 impulses. So you have to create a median set. function. Indeed, compute impulse response. Beautiful. This time we will create an impulse response function. What do you need in an impulse response? Phi s, I type, k, columns, q. Well, I type is situations, events, k is columns, q is moving average, p is autoregression, p lags, qp, p lags, p equals 2 or whatever. Phi is we're going to estimate. So construct psi, which is taking a vector 1 to q. Sum will start with 0 for j is equal to 1 to minimum of pi. So see, we're not going to use while here. Sum is sum plus reshaping the whole equation exactly. Then psi is psi and vectorizing sum transpose. We need to vectorize the transpose of the sum. Sum might have been a matrix. Now it will be a vector. Sum 0. Beautiful. So storing here the autoregressive moving over each parameter, and for I is equal to c pi vectorizing or as vector. The r is more beautiful. Simply as vector is what we need. Then impulse responses is simply S transpose. So remember why did we do transpose? Because so that the elements follow that order. So we have S now. The impulse is S transpose. Where is S? S has been mentioned before in our question. S is given to us, isn't it? Oh no, this is a function, so even if you don't have S, it's fine. S transpose so this is the regular impulse function. Impulse, Columbine impulse. We're familiar with this. So now we have taken all the elements of S, taken transpose of it. Then when we did transpose, we can get orders are maintained, and then we can get back. So if I type, if we pass a situation, then it will accumulate, otherwise it will not. So this is a regular impulse response function. Now let's go back to, so we have what? One more time. You'll estimate your autoregressive parameter as I type k qp. So sign restriction. So we have data coming into the system. Alright. We scale. We do lag matrix. Not necessary. We could have done the other way around, just like the previous example. But yeah, why not? We can also do lag matrix. So we did that. We did estimate in the first stage. We did OLS estimation, initialized. We estimated VC and everything. Then we are doing the regular autoregressive estimation. We did that too. So the only change with the very first thing is that our OLS estimation has trend. Whenever there is trend, there is some additional element in our X that we need to remember. The X equation will slightly change. Nothing else changes even by a nail up until Koleski decomposition. Then no regular impulse response function will be called here from our function that we have just mentioned. That function is the regular impulse response function. There is no game here. non-accumulated and orthogonal impulse response. Did we create two impulse response functions? Why did we construct? Yeah, we did. Why did I miss it? Oh no. Impulse response. So moving average parameter and impulse response. I've taken those down to the equations. That's all, nothing else. In the function. So we created a function with taking down the moving average part. So impulse will be created when you call with the no sign one. Now we generate theta, and use theta we generate Q matrix, and now we don't only estimate S but with Q matrix. So we have impulse rotation, call is Q, rotated by matrix Q. Fine. Now we need to do the iteration, and we need to select only those impulse response functions that satisfy sign restriction. And how do you do that? Which ones are to select? This is the part. We take impulse response values from the impulses, creating 4 sets of impulses. Then each sets of impulses are standardized by subtracting by median and dividing. So we take standardized impulse responses, and those which has the smallest absolute deviation from summing across all the impulses, those who has the smallest absolute deviation, those impulses are chosen with the smallest deviation. So we want to do iteration 100,000 times, zeros, Q plus 1 rows, 1 columns, because it will go 1 forward. And success, number of success 0, will pass this value to initiate iteration 1 to number of simulation. Theta is this, Q matrix is this, random number, theta is random number. So you are randomly creating run if 1, rows 1 column, run if 1 rows 1 column, not necessarily one element will create 1 row 1 column. That's the matrix. Impulse will now call S and multiply this Q mat with else. We'll continue to do that, because don't think about iteration now, number of iteration, just think about theta, Q mat, and theta that generates Q mat with random number, and multiply S with random number, and choosing the impulses. So this creates the whole 100,000 impulses. If minimum, so command true KQP impulse 1 or true, 1 or true, go back to impulse function. What is 1? I type 1. I type is the long run. The long run is true in R, not 1. In R, I type is true. Good, not bad. Because how did we satisfy R I type here? Impulse apply. Just true. Then if our impulses are greater than 0 and the 1, 2 and 4th of impulses, minimum of these impulses are greater than 0 or 3 is less than 0, the minimum is less than 0, this is OR, right? What is the function? What is the logic here? If this one is greater than or equal 0, or this is not AND, this is OR. Yeah, what is that mean? Still we can look for it. so it will go on. So basically, an aggregate supply shock has positive effect on output and negative effect on prices. Aggregate demand shock has positive effect on both. So 1, 2, the third element, the aggregate supply shock, aggregate demand shock. So the third element is negative, everything else is positive. That is what the logic here is. Very simple. 1, 2 and 4, if they are greater than or equal to 0, and the third one, minimum of that impulse, minimum of that impulse, even twice, I'm taking the minimum twice, is less than 0. So we are taking a minimum of this impulse and taking the minimum of those minimum, the minimum of the impulses, and taking the minimum of those minimum impulses. If they are greater than or less than, then we have impulse select and impulse. If that is true, then our rows are, our columns are impulse select, column bind, impulse select, and impulse. So there you have impulse and there you have impulse select. So zeros and then impulse. So one, the first one is the zeros one, the regular one that we always set. The zeros, impulse select 0, q plus 1 1, and then impulse. Number of success is number of success plus 1, because there is a loop, it will go on by 1. Number of success will continue to increase from 0. To see how many iterations we have done, actually, that is the purpose of these two code is this, to see how much of the iteration is done. All right. 1 to number of simulation. Did we create zeros? Probably not. That will slow down the system. We could have created a 0 to store the data. Anyway, oh no, we have impulse select zeros, q plus 1 rows 1 column. That should work. That should work. Impulse select has zeros, that will store. See, yeah, the loop function is storing that. Okay, and then we closing it. So we have number of success divided by number of simulations. So number of success is median by standard deviation. So taking the minimum of both conditions, we take the median divided by the standard deviation. Basically what we're doing is that we're doing this absolute deviation from summing, the smallest absolute deviation from summing across the 4 impulses. So smallest absolute deviation is being taken. Find the model that correspond to median impulses for all values. So this is all values. Median impulses is everything except for the first one. Choose contemporaneous impulses, which is number of success and columns y2. Really? Contemporaneous impulses. Okay, reshaping. I impulse, Z impulse. I'm really not interested from here on. Taking total and taking the median and overall median impulse. Choose the set of impulse which is the minimum absolute total deviation. So these are important for sign restriction. Just have a look. Median. So taking impulses. So first we're reshaping this first row, all columns, to number of columns. This is the rows, this is the number of columns, taking number of columns, and then contemporaneous impulses, standard deviation. This is another important equation. Contemporaneous impulses. These are the number of rows squared. This is the number of columns, because we are actually squared to have a square matrix, rows and columns. Then standard deviation, then median. Here the median and standard deviation is done in a very bad way. We'll probably not do that. Z impulse. The fact is, you don't actually need to do anything that is mentioned here. You could just find this, which is reshaping our impulse select matrix, taking only the first row bind, right? Then only the first row in rows by the number of rows and number of columns set as this. Then you can just do z-score function. Call the z-score function. That will do the thing for you. Total is taking row sums, sum of the impulse, or taking row sums, transpose row sums. Choose the set of impulse which is the minimum. So from the z-score, taking the summations, the minimum of the summations we take, and the median sum impulse, so minimum of those we take, and then the median is this equation. This is another important one, I guess. All rows, number of columns is what changes by 2 plus 1. Okay, 5 minus 1 by 2 plus 1 to 5, I mean square, okay, whatever. So the last few parts I'm gonna leave one, maybe just for this I'm gonna leave it on for 2 minutes for you to have a look. But that kind of concludes our situation here, SVAR discussion. Maybe given enough time I can discuss further on sign restrictions. However, up until variance decomposition is not difficult, and updating the variance decomposition is not difficult. Iteration is not difficult as well. Iteration is quite simple. With the functions, iteration is not at all difficult. The conditions is where the difficulties start to crawl up, and they become a bit bigger when we are gonna start going down with the dimensions. And still it's not gonna be that difficult, but for beginners it's a bit difficult to remember, so it's better to just memorize the contemporaneous impulses to find the contemporaneous impulse equation to some extent, right? So this is X, rows by rows, reshaping by rows and by columns. This is the number of rows I want, which is the size of columns divided by size of column squared. Generally there are 2 divided by 4. Number of rows I want, and number of columns I want, 4. So this helps me to find how many of contemporaneous impulses are there. Then I do z-score. You don't need to do this, just z-score should be fine. Z-score equation should be fine. I'm not sure what is equivalent z-score for equation in R, but in MATLAB is simple z-score. And then there is finding the total, finding the minimum of the total, and then again another median, which makes it a bit more difficult to again one more time. So there you have sign restrictions, and we could have gone into Okun's law, but maybe if time permits we'll sometime look back into that, and that is not necessary to some extent. It's only playing with the number of restrictions. We cannot practically have go through all these problems, just the ones that are most important. Thank you very much for your patience with structural VAR. Next coming is latent factor models, or what should I say, recursive Kalman filter algorithm. Very important, very interesting, the mother of artificial neural networks. Thank you very much.